Okay, so unit 1 was all about rational power and root functions, okay? So things like square roots, things like fraction functions, things I can graph. We talked about a bunch of different horizontal asymptote rules, vertical asymptote, x-intercepts, y-intercepts, all that stuff, I should say, had to be done by hand. On your final, you will get to use a calculator. So that is nice. However, on your final, for like the graphing problem, you will have to actually tell me what the x-intercepts are, y-intercepts, what the vertical asymptote and the horizontal asymptotes are, in addition to graphing it. It's not just going to be points for graphing it, if that makes sense, okay? So kind of just a quick recap. If you are asked to find your domain is all of your x values, your range, all of your y values. If you are finding x-intercepts or y-intercepts, you either set the numerator equal to 0 for x-intercepts, or for y-intercepts, you plug in 0 and solve for y, and make sure you write them as a coordinate, okay, for x-intercepts and y-intercepts. Your vertical asymptote is just found by setting your denominator equal to 0. And then here's where all these rules come into play. This is probably something important to put on your note card that you guys get to use on your final, about degrees of the numerators versus denominators and how those relate and what does that tell us about the horizontal asymptotes, okay? So if it's larger on top than on bottom, it's no horizontal asymptotes. If it's less on top than on bottom, then it's y equals 0, so that's the x-axis. If it is equal to each other, that's the ratio of the leading coefficients. So like, for example, because I'm not going to do one like this, if I had something like y equals 4x squared over 2x squared, okay? If the degrees are exactly the same, this would mean that the horizontal asymptote would be at y equals 2, or 4 divided by 2, okay? And then if it is exactly one more than the degree of the denominator, there might be a slant asymptote, which means you would have to divide, okay? And then last thing about graphing that we got to take into consideration is if there is a hole occurs if you have a factor that is both in the numerator and in the denominator. If they cancel out, then there is a hole at that specific x value, okay? It is not defined on the graph at that point. The graphing calculator, if you look at the graph, it will not show you that. If you look at the table, it would show you that at that certain point, but that's something that you're going to need to know how to do, okay? So we're going to do one example of this. Again, I can't do an example of every single type, but the other two that are on your final are pretty good examples to try out as well. Okay, so I want to find my horizontal asymptote, vertical asymptote, x-intercepts, and y-intercepts. And then the rest of it, we'll let our calculator do the work. Vertical asymptotes we find by doing what? Setting the denominator equal to 0, okay? So I'm going to set this equal to 0, which let's just like real quick factor this. So if I factor this on the denominator, I would have 2x and x. Then I want to multiply to give me -6, add to give me 5. So that would be a +3 here and a -1, okay? So now I can set the denominator equal to 0 a lot easier, and I can see that my vertical asymptotes, there's going to be 2 of them, and they're going to be at x equals 1/2 and at x equals -3. Remember, for your asymptotes are going to have dashed lines, not solid lines when you are graphing them. Horizontal asymptote, I'm going to look at the degree. So the degree of the numerator here is 1. The degree of the denominator is 2. So if I go back to my rules, if it is less on the top than it is on the bottom, so my numerator is less than the degree of the denominator, then my horizontal asymptote is what? Yeah, 0. So y equals 0. And again, asymptotes should be an equation of a line, so it should be x equals and y equals. Now, x-intercept, if I wanted to find the x-intercept, I'm going to set what equal to 0? The numerator. So I'm going to set x plus 1 equal to 0 to get my x-intercept of -1, 0. Always write that as a coordinate. And then lastly, my y-intercept. For y-intercept, I'm plugging in 0 for x. And when I plug in 0 for x, I end up with 0 plus 1, so 1 on top, and then a -3 in the denominator. So your coordinate would be 0, negative 1/3. Okay, those will be the 4 things that you have to fill out on your test. And then from there, we're just going to graph this stuff, and you guys are going to draw a quick sketch of what that looks like on the graph to get the rest of the points, okay? So I'm going to draw my vertical asymptotes first at 1/2 and at -3. And then my horizontal asymptote is at y = 0. And then I can plot those 2 points of my x-intercept and my y-intercept. Okay. One other thing to remember about vertical asymptotes and horizontal asymptotes is vertical asymptotes we can cross. Horizontal asymptotes sorry, that's wrong. Rewind. Vertical asymptotes we cannot cross, okay? Horizontal asymptotes you can sometimes cross. So I've kind of got 3 different quadrants here of my graph. I've got to the left of the vertical asymptote, in between these 2 vertical asymptotes, and to the right of this asymptote. Okay, so I need to see what's happening on all of these intervals. So in your graphing calculator, we can go ahead, on your graphing calculator, in y1, you can go ahead and plug in this function. Okay, if you plug in that function in y1, and then look at your table, that allows you to see all of your x's and y values. And obviously you can also just see what the graph is, right, by looking at the graph. But I need a few points to be able to plot my graph here by hand. So I need at least 1 point to the left of this vertical asymptote. So the left of that vertical asymptote would be a point at -4. So I want to look at -4 on my table. I also want to look to the right of my first vertical asymptote there after the y-axis. So I'm going to we can plug in 1 or 2. And then I want to know what is happening in between here. I know that I'm going to be going down towards this vertical asymptote, but what's happening over here? Is it going up or is it going to go back down? Okay, I'm not sure. So on your graphing calculator, it should show you. But again, let's test that point of -2 on our graphing calculator to find out what that actual value is. So if you find all these values on your calculator, there are going to be some small decimals or fractions depending on how you have your stuff set up. So I got like -3/15, 3/15, and 1/5 for my answers there. So I'm just going to plot those points, and then I can go ahead and draw my graph. So at -4, I'm just down here a little bit. And your graph should be approaching both of those asymptotes. At -2, I'm just up positive a little bit so I can see that I'm going towards that vertical asymptote now on the left. And then on the right, I'm at just a little bit above the x-axis. And I know that I will be approaching both of those asymptotes. Again, you get to use your calculator, so your graphing calculator will be very helpful on this question. Okay, so that is our graphing of a rational function. So it's a fraction, that's why it's rational. There are 2 other examples of this on your finals review that you will want to make sure that you do, okay? Because your finals review is worth 15 summative points, okay? It's based on completion. Answer key is posted so you can check your work, but not all of the work is shown. So you need to make sure you're kind of spending some time of that over the weekend here. Okay. Next thing that we talked about in section or unit 1 was solving rational equations, okay? We do need to first look at, though, is there going to be a whole or is there anything that makes the denominator equal to 0? Because if so, then those 2 things are called, that makes it undefined, right? So we can't have those answers as part of my solution, so we have to omit those. So like for this first example here, this denominator cannot be equal to 0, right? Because I can't divide by 0. So what can x not be? If I said 2x plus 1 equal to 0, I would get -1/2, right? So x cannot equal -1/2. And then now we can just go ahead and solve it. So I would just think about this as like 1 over 1 and just cross multiply. So I've got x plus 2 is going to equal 2x plus 1. And just a nice little algebra problem here. Get your x's on one side, move your numbers over to the other, and we get x equals 1. Now, I didn't need to cross anything out because negative 1/2 was not what I got as my solution, so we are good. 1 is our answer for this problem. Okay, number 2, I've got 3 fractions. So anytime you have a bunch of fractions, we want to get rid of the fractions by multiplying by what we call the least common denominator, okay? So if I look at x squared minus 4, I can think about factoring that as x plus 2 and x minus 2. So if I multiply this entire function by x plus 2 and x minus 2, will that get rid of all of my fractions? Yeah, right? So it's going to get rid of all of my fractions, but before we continue, I want to say, what can x not equal? What makes the denominator equal to 0? 2 and negative 2, okay? So I can't have those two answers. So let's go ahead and start multiplying here. So I'm going to multiply this x plus 2x minus 2 with this whole function here, or this x over x minus 2, to give me x times x plus 2, because the x minus 2s would cancel out. Okay, then I take this whole thing and multiply it by my second term. The x plus 2s are going to cancel out, and it's going to be left with just 1 times x minus 2. And then lastly, multiply this times my last fraction there. My denominators are going to go away completely, and I'm just going to be left with 8. And now this just becomes an algebra 1 problem. We just got to distribute here and solve for x. So when I distribute, I get x squared plus 2x plus 1x minus 2, and that equals 8. When we've got quadratics, we want to get everything equal to 0, so that way we can factor or solve it using our calculator. So that's going to give me plus 3x minus 10 is equal to 0. And again, once you have your quadratic and it's equal to 0, I can either factor it or I can use my calculator. Either one's totally fine. This one's a pretty quick and easy one to factor, so I'm just going to factor it. X plus 5 and x minus 2 is what I get when I factor it. So I get my answers to be negative 5 and positive 2. Now, are both of those answers for this problem? No. I got to omit one of them. I got to omit 2 because I can't have 2 in my denominator. Otherwise, I'm dividing by 0. We can't do that. So our answer is just x equals negative 5 for this one. Okay. Moving on, if I'm asking you to find the domain and range, or for this one it's actually just the domain of each function, I have to remember 2 rules, okay? The first rule is that if it is an even root, that root has to be greater than 0. So if it's even, we have to be greater than or equal to 0, because I cannot take the square root of a negative number, okay? That will not give me a real solution. If our root is odd, the cube root, the domain is all real numbers. So for example A here, I do have the square root of 4x plus 12. That is an even root, okay, because it's a square root. Now I'm just going to set the 4x plus 12 greater than or equal to 0, and I'm going to solve this. To be x is greater than or equal to negative 3. If it did not specify to write it as an interval notation, you can leave this as your answer. Otherwise, if I wanted to write this in interval notation, I would have from negative 3 to positive infinity for my solution. Okay. Now, I will say that there is one on your review that has a quadratic on the inside of your square root. Make sure you go and try out that problem, as you should be anyways, but there will be a problem like that on your test. Again, I just can't give an example of every single type that you might see. So I'm giving you the basics of everything. Okay, this one here, I've got the cube root of negative 8x plus 8. It is an odd root, so that means my solution is all real numbers. So from negative infinity to infinity. And that's it. Any questions about the first page so far? I know we're going through stuff fast, but this is hopefully a review, a good review for most of us. Yeah, okay. All right. Next one here, we are solving equations with roots, okay? So again, we still need to remember that if we have square roots, there is some restrictions on our domain. So like for the first one here, if I'm looking at this, if I'm looking at the square root of 11 minus 1, the square root of 11 minus x, this has to be greater than or equal to 0. Okay, so my answers for x actually have to be less than or equal to 11 in order for them to be true. Okay, otherwise we will have to omit those solutions. So whenever you're solving square roots, go ahead and isolate your square root unless there are two of them. We'll talk about that here in a second. But I'm going to go ahead and move that x over to the other side. So I have square root of 11 minus x equals 1 plus x. Undo a square root, I can square both sides. And now I'm just left with 11 minus x is equal to, and we are going to have to FOIL this out. So when I FOIL this out, I get x squared plus 2x plus 1. Set this equal to 0. And I get minus 10 there. And this one we actually just factored on the previous page. It factors into x plus 5 and x minus 2. Again, you could just use polysmelt 2 here and just factor it on your calculator to find those roots. So my answer is both negative 5 and positive 2. Now, are both of those numbers less than or equal to 11? Yeah, so I don't need to omit any answers. Okay, example 2 has 2 square roots. If I just go ahead and square the left-hand side and I FOIL with 2 square roots, that's going to be pretty gross, yeah? So instead, let's have 1 square root on both sides. So I'm going to add the square root of x plus 1 to the other side and be left with the square root of 2x plus 3 on the left. And then I'll have 1 plus the square root of x plus 1 on the right-hand side. Okay, and now let's go ahead and square it. It's still going to be a little gross on the right-hand side, but it will be better. So the left side, those square roots go away, and I'm just left with 2x plus 3. And the right side, you're just doing 1 plus the square root of x plus 1 times itself. So you are going to have to FOIL. And when I FOIL, I get 1 plus, how many square roots of x plus 1 am I going to have? I'd have 2, right? So 2 square root of x plus 1. And then when I multiply these last 2 terms together, I'm just left with x plus 1. Okay, we still have a square root, which means we're not quite done. We need to move all of our x's over to one side, all of our numbers over to that side. We want to isolate that square root again. So I'm moving everything over to the other side. Minus 1, minus x. So I'm subtracting 2, and I'm subtracting an x on the left-hand side. So I'm just left with x plus 1 is equal to 2 times the square root of x plus 1. Now, technically I could divide by 2 here if I wanted to, but I think it's just easier to just get rid of the square root right now. So let's go ahead. We have to square both sides completely. And this is where some people get confused. You have to square the 2 as well. It's in front of your square root. So on the left side, do a quick little FOIL. We're left with x squared plus 2x plus 1. And on the right side, that's going to equal 4 times x plus 1. Okay, again, now it just becomes an algebra 1 problem. We need to distribute and get everything on one side. So I've got x squared plus 2x plus 1 equals 4x plus 4. So I've got x squared minus 2x minus 3 equals 0. And once we've got our quadratic equal to 0, we can plug it in our calculator, polish, melt, or solve it by hand. Either one works. This one's, again, another pretty easy one to just factor. And this would give me my answers of x equals 3 and x equals -1. Now I got to double check, do both of those answers fit in my interval or in my domain solutions? If we look at this, 2x plus 3 has to be greater than or equal to 1. So my x has to be greater than or equal to -3 halves, right? Are both of those greater than -3 halves or -1.5? Yeah, -1's bigger than -1.5. And then this one here, x plus 1 has to be bigger than 0. So that means x has to be greater than or equal to -1, which it is in fact, right? So both of these answers are good, right? We don't need to omit anything. Those are two parts of my solution. Okay, Unit 2 is all about inverse exponentials and logs, okay? You will have to graph a log function on your test and then do a few of these other things as well. So just kind of two definitions up front. The horizontal line test, it tells us if we draw a bunch of horizontal lines on a graph, if it only crosses the graph at one point, then it's called a one-to-one function. If I want to test to see if something is an inverse, I have to do two compositions. I have to do f of g of x. I have to check to see is that equal to x. And I also have to do g of f of x. Is that equal to x? And if it is, then we have shown that these are inverses of each other. Okay, so let's look at an example of that. I've got these two functions here. We're going to define or find out if these are both inverses. So I'm going to take this g of x and I'm going to plug it in for x and see if it simplifies to give me just x. So I've got the cube root of x plus 1 all to the third power minus 1. Well, the cube and the third power, those cancel out. So I've got x plus 1 minus 1, which gives us x. So that is good, right? And the next one I'm going to do is I'm going to take this whole function and I'm going to plug that in for x. So I'm going to be left with the cube root of x cubed minus 1 plus 1. And if we simplify that, I've got the cube root of just x cubed because the minus and plus 1 go away. And the cube root of x cubed is just, in fact, x. So we've shown both compositions give me x, so therefore these are inverses of each other. Okay, next example is to actually find the inverse of the function. Okay, we're given a function f of x equals the square root of x plus 5. If I want to find the inverse, that means I need to switch my x's and y's. So I'm going to go ahead and plug in for y. I'm going to have x equals the square root of y plus 5. And now I need to solve this for y. So I'm going to square both sides. I have x squared equals y plus 5. So y is going to be equal to x squared minus 5. Okay. Or another way that you might see this written is f inverse of x is equal to x squared minus 5. Domain and range, again, if we're looking at our regular function, the regular function domain and range are found first by looking at, well, what makes the stuff underneath the square root greater than or equal to 0? So when is x plus 5 greater than or equal to 0? Well, when x is greater than or equal to -5, right? So my domain for the function is from -5 to infinity. Okay, if you weren't sure on your calculator, you could graph this and see where is the farthest left point. You should also kind of have an idea of the square root graph looks something like this, right? It's like half of a parabola on its side. Which means that my range, if there is no shift up or down of this square root graph, my range starts at 0 and goes up to infinity. Now, if I'm talking about my inverse function is just going to be the exact opposite. So my inverse function's domain is the range of the regular function, so from 0 to infinity, and then my range would be from -5 to infinity. Because this is kind of an idea, this one that I drew here in black is basically what the square root of x plus 5 looks like, a sketch of it. My inverse function looks something like that. Okay, these next two, we're just gonna rewrite. We're not actually gonna solve. I just wanna rewrite this in exponential form. Okay, so given my base of my log, I'm gonna take that and make kind of a little loop-de-loop here. So I've got 8 to the x power is going to equal 4. Letter B again, I start with my base, go up to the other side, and that equals 16. So I've got x to the 4th equals 16. We could solve those if we wanted to, but we really only care about the rewriting for the final, okay? So these next two are about compound interest. These would be two formulas that would be good to write on your note cards, probably. So your formula for compound interest is here. A equals P times 1 plus R over N to the N times T power. Remembering that N is actually the number of times it's compounded, and R is your rate as a decimal. Okay, so if you have 3%, it's 0.03. So this example that you're given on this is just a pretty straightforward example. You're plugging in the numbers, plugging in your calculator. There's a few on your final exam review where you have to solve for the rate. So there's a little bit more algebra involved there, okay? But this example, we're given $1,000 invested at a rate of 4%, compounded quarterly. How much will be in the account after 10 years if no withdrawals are made? So I'm trying to evaluate A, or the amount accumulated, and that's going to be equal to the amount I invested, or 1,000, times 1 plus my rate, divided by how many times is compounded quarterly? 4 times a year, to the power of 4 times 10. Okay, and if I evaluate that, plug that in my calculator, I end up getting 1,488.86. Okay, the other formula that you might want to add on there is your compounding continuously, so your PERT formula. Another straightforward example here. We've got $5,000 deposited in an account paying 3% compounding continuously. How much are you going to have after 5 years? So my amount would be equal to 5,000 times E to the 0.03 times T, or times 5. And if I plug that in my calculator, I got, again, approximately 5,809.17. Plug that in your calculator, check to see at some point that you get the same answer as me. But we will move on. Graphing logs. Again, when you're graphing these functions, I will need to see what the asymptotes, x-intercepts are, and oh yeah, on this one we're gonna write out what the domain and range are as well. So, I don't know about you, but I don't know what log base 2 of a number is. So we're gonna rewrite this as an exponential, and that's kind of the first step for all of these for graphing logs, is to rewrite as an exponential. Okay, so this is gonna become 2 to the y is equal to x minus 1. 2 to the y equals x minus 1. Okay, let's get this solved for x, because now I can actually evaluate some points for y and get some out points for x. Okay, also just a reminder, exponential graphs. An exponential graph looks something like this, whereas a log function is going to look something like this. Okay, so your exponential is going to have a horizontal asymptote, so you can look at your transformations that way from your graph of an exponential, and your log function here is going to have vertical asymptote. Okay, so looking back at the original function, I can tell what the transformations are that are happening to this. So if I have x plus 1, that means I'm shifting my entire log function which direction? If I'm minusing it. I'm shifting it right 1, right? So this right here tells me I'm shifting right 1, which means that my vertical asymptote that normally is at 0, or the y-axis, the vertical asymptote is now going to be at x equals positive 1. That's where my vertical asymptote will be at. Okay, and then from here I just need to find some points. So x and y, let's find some points here. Is it going to be easier to pick points for x and evaluate y, or pick points for y and evaluate x? Pick points for y. So let's just pick a few points. -1, 0, and 1. If I plug in -1, 0, and 1, I will get an output. Let's see. So 2 to the 0 is 1, plus 1 is 2. 2 to the first is 2, plus 1 is 3. And then 2 to the -1 plus 1, that would give me 1.5. Because I already know the general shape of what's going to happen, so as long as I've got a few points, I can graph this pretty easily. So on our graph, I'm going to draw my vertical asymptote at 1. Again, dotted lines for your vertical and horizontal asymptote. And then I'm just going to plot those points. So I've got 1.5, -1, 2, 0, and 3, 1. So I know that it's going to approach that vertical asymptote, but it won't cross it. And then I know it's increasing at that rate to the right. So now identify my domain and range. My domain is all of my x values. Okay, so this is a case where I cannot have an x value of 1, right? So what am I going to have around my 1? A bracket or parentheses? A parentheses, right? So my domain starts from 1 and it goes all the way to infinity. I start here and I go all the way to the right. My range is all of my y values. So my range of this function, how far down do I go? Forever. How far up do I go? Infinity, right? So my domain is -infinity to positive infinity. So this would be a case where you would not have a bracket around your domain for your log function. Okay, moving on to solving with some logs. First one here, if I have exponents in the, if I have variables in the exponent and I want to move them down in front, I'm going to have to take the log of both sides or the natural log of both sides to get those to move down. So I like natural log just because it's one less letter. So I'm going to take and move this down with my natural log of 2. Okay, if I move this 4 minus x down in front, that's 4 minus x times the natural log of 3. Now, can I get just x on one side right now? No, I'm going to have to do some distributing. Okay, this natural log of 2 is just like a number, so I'm going to treat it like 1. So I'm going to distribute natural log of 2 to both terms. I'm going to distribute natural log of 3 to both terms. So this is just a number. Okay, now can I get all my x's on one side? Yeah. I'm going to add that x from the right side over. And I'm going to move that natural log of 2 over to the right-hand side. Okay, but I'm solving for x, so what do I need to do now?
Don't you divide by like 3 and 2?
Yeah, we totally are going to divide, but we first need to take that x out. So let's take an x out of both of those terms on the left side. And then now that I have my x by itself, I can do exactly what you're saying there of dividing by the 3 natural log of 2 plus natural log of 3 on both sides. So I would highly recommend making a fraction when you're typing this into the calculator, but you will approximately get 1.16. So I'll give you guys a minute quick if you want to try plugging that in. Okay. Before we can solve this, we have to remember our log properties, what we can do when we have the addition of two logs with the same base. If I have two logs with the same base and I'm adding them together, what operation do I do? Multiplication. So I'm going to rewrite this as log base 10 of 3x plus 2 times x minus 1 equals 1. Okay, now if we have a log, I need to rewrite it as an exponential to solve it. If I have an exponential, I usually need to use some logs so that I can solve it. So this is actually a base 10. So I can think of rewriting this as 10 to the 1 power is equal to everything right here. So I've got 10 to the first is equal to 3x plus 2 times x minus 1. And now it's just a little bit of algebra. So I'm going to go ahead and factor this and get everything equal to 0. So I've got 3x squared minus 3x plus 2x minus 2. Move that 10 over. Combine my like terms. And I'm left with 3x squared minus x minus 12. Now, is there anything I can multiply to get to negative 36, add to give me negative 1? I don't believe so. So, we can either use the quadratic formula, or I would use the go to apps, go to polysmelt 2, and then go to root finder to identify your two values. And when you plug it in, you do get, and I would try this out yourself, but you do get 2.7 and approximately negative 1.84 for your two answers. Okay, but with like anything, solving equations and things, we got to make sure that our answers both work. So if I go back and look at my domain of both of these, my domain of 3x plus 2 has to be greater than or equal to 0, okay, for both of these. Or x minus 1 has to be greater than or equal to 0. If I solve both of those, I get x is greater than or equal to negative 2/3, and x is greater than or equal to 1. So which of my two answers am I going to have to get rid of? Yeah, the negative 1.84. Okay, so my answer is just the 2.17. Now, after units 1 and 2 on your final exam review, you should for sure be comfortable doing 1 through 4 and 13 to 62. Okay, answer key is posted for all of those. Again, not all of the work is shown for all of them. A few of them have work shown. But if you see any mistakes, let me know. I know of a few already, but I still need to update the key. So if you see any mistakes, please let me know so that way people are studying the correct stuff.